Okay, so we are jumping into geometric optics. We know that the light is an electromagnetic wave and its wave properties are important for things like polarization and later diffraction interference. But when it comes to how does the light bend through things or bounce off of things, it's useful for us to just talk about it in terms of geometric rays. So there are two laws that we have to consider. The first one will be the law of reflection. And this means the light hits a surface and bounces off. A few kind of conventions and vocabulary words. This will be our interface, and all angles are measured relative to the normal line, or this perpendicular line that's perpendicular to the surface. We have a ray that's incoming. It's called the incident ray, which is just a fancy way of incoming, or, it's what caused the incident when it landed here. Its angle would be measured there relative to the normal line. It'll bounce off or reflect. So this will be our reflected ray. And it's also got an angle. We'll call it the reflected angle. And the law of reflection is a tough one. The incident angle is exactly equal to the refracted angle, or reflected angle. So that's it. There's really nothing else to that problem. That means that anything we invent for you is pretty much a geometry problem of just tracing the lines of the reflections and keeping track of angles. The hardest problem I can think of is the funhouse maze of mirrors, right? And there's a few of these in your book where how would you deal with it? You just have to follow the light as it bounces across each of these surfaces and goes through the funhouse maze. So you can do that on your own. I think it's one of the book problems. You get so excited. The other one is a little bit more involved. This is the law of refraction. And refraction is just a fancy word that means it bends when it reaches that material. So two things that we know about light when it's incident on a transparent medium. Here we'll have the light ray come in. And here it comes out, and it gets bent in some particular direction. The brain is a little stupid about this kind of stuff, and it would expect for the line to just go here in a straight direction. But depending on the differences in the indices of refraction, these values, or how optically dense the material is, if you go from low into high, the refracted angle bends toward the perpendicular. So what we're trying to say is this. You would expect it to go straight through, but it doesn't. If you go from low to high, it gets caught and bent more toward the normal line. Okay, in the converse, let's say we went from a 1.5 into a 1.0. So I went from something more dense into something less dense. In this case, we expect the ray to bend away from the normal line. So from high to low, it bends away. Like that. Okay, so these are things that you just have to kind of commit to memory. We have to just know low to high bends toward, high to low bends away. So a question, why is that the case? Well, actually, I've learned this from a student. So we talk about the ray being infinitely thin, right? Like just a single ray. But let's give it a little bit of thickness and make it incident on this surface. And if it's got a little thickness, maybe we can think about it like a car or some kind of vehicle that's got some wheels. And we've done experiments like this before. Let's say this is the paved asphalt, and this might just be sand or gravel or something in the road. These wheels are going at a particular speed, but this one, it's harder to get through the sand or gravel. It reduces the speed of this one wheel. So what do we notice the car does naturally? As soon as it engages, that wheel slows down, the rest keep pulling forward, and it has a tendency of jerking the car into that material. So the net result is, because this part of the ray slowed down first, it kind of had the effect of bending or pulling the ray into the more dense material. So we can see that in kind of going from an easier to a more difficult to traverse medium, the light would do the same thing. So you may have some objection, wait, what do you mean the light slows down when it goes into the different mediums? Well, let's think about where the speed of light comes from. It's 1 over the square root of epsilon naught mu naught. And these two parameters were kind of how easy space can pick up and hold these fields, whether it's electric or magnetic. So let's say I had some kind of a glass, like in a parallel plate capacitor, that would have not just an epsilon naught, but it'd have an epsilon with a dielectric constant, right? This is how easily space can pick up and hold a field. This is how easily glass can do it. Right, so that might translate into something like K, epsilon naught mu naught, and because this number is always greater than 1, the denominator increases, and what's that do for the speed? It decreases. If we want to do this a different way, and let's say I had some kind of exotic material like, I don't know, transparent iron, well, it's got a different mu value, and that was related, of course, to its relative permeability times the permeability of free space. Well, that number is also greater than 1. So I could have my speed also lowered. The speed inside any material that is not just empty space or vacuum is always less than c. I don't have a material that when I shine a light into it, it suddenly becomes super luminous and invents warp drive. It's insanity. So what do we want to call this metric for measuring how easy light can get through a material? That's called the index of refraction. And that value is really just the ratio of the speed of light to the speed in the material. And as we know that the speed of light is always c, and then v is always greater than c, or is always less than c, I'm sorry. I'm in a warp drive kind of frame. Then we know that the index of refraction is always greater than 1. It's 1.0 if you're at light speed, and everything else that has a slower speed will have a larger index. Okay, vacuum is, of course, 1.0. Air is, I think, actually 1.003. But you can just approximate that and say that air is a vacuum. We don't really see real effects from the index of refraction of air, especially comparing it to glass. This is such a small value. The only time I can really think of where this would become important is if we were comparing, say, air to true vacuum. So right at the interface between the atmosphere and space, maybe this would start to be apparent. But here on Earth, with other materials that are like 1.1, 1.5, this is going to be a very small contribution. So we can approximate. Do you need to memorize a big table of indices of refraction? No. There are only 2 that you should know. Say that air is about 1.0, and water, because it turns up so often, is about 1.33, or 4/3. I don't expect you to memorize the index of refraction of benzene or oil or glass or acrylic. Forget that. Air and water are the 2 big ones. Any of the other ones we should be giving to you as a reference. Okay. So, what is something that may be interesting to note about the index of refraction of a material? It's not the same for every wavelength, necessarily. So if we have something that has kind of a wide, let's call it a deviation in the indices of refraction, let's say it's kind of wide, and that means n for one wavelength is not the same as n for the other wavelength, and they are different by a pretty substantial amount, then it's possible for us to see that difference expressed. So let's have a light ray come in, and it's going to interfere or interact with some kind of larger index of refraction n. One color or one wavelength of the light might get bent some amount, but the other colors are going to get bent different amounts. And if our device is large enough and we give the light plenty of room to spread out to where we can discern the different colors, you guys will see a dispersion or spreading of all these different wavelengths. So this is something that would happen in a prism. And the refracted angle for blue or purple is not the same as the refracted angle for red. If this dispersion relation, or if this difference in the index of refraction was narrower, then this rainbow would be tighter. And if it's tight enough, it might look white. And you may not see any of the colors separate out. You might only be able to see little bits of red or blue, but all the others are still overlapping and appear white. This is something that is visible in the difference between a diamond and a cubic. Diamonds have a very small window for its index of refraction. So when the light goes into the stone, bounces around and comes out, it still looks pretty white on exit. But for these cheap costume jewelry, the cubic has a wider variance in N. So when the light comes in and bounces back out, you see a lot more actual rainbows and a lot more color in the flare that comes out. So that's kind of not desired. Okay, I guess we went on a tangent but never really covered what is the law of reflection again? So we know that light bends, and we have an idea now of what index of refraction is. So when the light comes in, we just have the incident and the refracted. And this will be the incident and the refracted indices of refraction. So it's actually got a special name. It's called Snell's law. And it goes like this. N times the sine of the angle on one side of the interface equals N times the sine of the angle on the other side. I learned it this way first. No. Ni sine I equals Nr sine R. And this is a fine way of keeping track, right? One side of the interface, everything is incident. The other side is refracted. Do your comparison before and after and run through the equation. There may be situations, though, where you have multiple layers on top of each other, right? So here's N1, N2, and maybe N3. And you get all kinds of behaviors at the different interfaces. In that case, I like to maybe just number each one, and then I can keep track of them that way. This is a perfectly good method, too. My favorite way, though, to make sure I don't reverse the order or somehow get confused, I tend to label things by what is the medium that they're in on each side. I mean, this to me is idiot proof. It helps me keep track of what side am I on of the interface, and whatever. I don't really care how you subscript and index these different sides. Just do whatever makes sense to you, whether it's by their behavior, their order, or by what they're made of. Okay, so let's see, any special conditions or special cases that we should worry about? I know that if I go from a high, into a low, so let's draw this, I'm going to see the ray get bent away from the normal line. Well, here's a question. What's the maximum amount that it can get bent away? This would be a case where your refracted angle is 90 degrees, right? So this might be an interesting question. What is this special incident angle, or let's call it a special critical angle, where this condition is first met? I might do N2, or N whatever this is, N high, times the sine of that angle, which we think is critical, equals N low times the sine of 90 degrees, which is just 1. So theta C is this ratio of low to high, and it's got the inverse sine If you've seen that equation in the book, here's where it comes from. Don't memorize this. Just remember, oh yeah, this is how to do Snell's law, and this side just happens to be 1. Now, what is critical about this? In one case, you have actual refracted angles. In the other case, the angles become imaginary, and an imaginary angle is non-physical. So if you have a ratio where these end up flipping or something, the angle that comes out would be an imaginary number. Turns out 2 things happen when you reach an interface. We talked about both. One is refraction. So some component of this light, some amount of the intensity might be refracted through. And another part is reflected. So there could be a balance, right, between how much is reflected versus refracted, depending on the incident angle. All angles lower than this, I know I get real ones. All angles out here, I get these imaginary ones. So if there's no refraction, what's left? Only reflection. And this is a condition for what we call total internal reflection. So all the light that hits the surface bounces back in. And that's just kind of an interesting phenomenon. I can think of a few incidences where you might use it. Some are important and some are kind of not. The not important case is dealing with gemstones. They're cut in a particular way that takes advantage of the index of refraction so that when light comes in, it strikes the back surface, it bounces to the next surface, and then it bounces back out. And we want this to be totally internally reflected so none of the light escapes, and it effectively kind of collects all the light and then retransmits it back out. So that's what gives it kind of its fire and its brilliant glow, and it's designed to take advantage of that in all the facets are kind of intended to take advantage of this phenomenon and spit it back out. So let's say that your gem cutter is asleep at the wheel and just does a bad job and cuts this way too deep. And remember, this was about the angle that we expected before. The light would come in. It'll strike this at a much more glancing angle, which is a good thing, right? That's outside of the critical angle. So it is still internally reflected, but it doesn't hit the next surface where we expect it to. Well, now this is clearly not internally reflected, and it'll refract out. Or at least most of it refracts out. So this is a stone that just doesn't pop. And here's another one where we are cut too shallow. Here we strike, and we are well within the critical angle. So it gets out immediately and doesn't have a chance to do its bounces. So these are just bad cuts, and one of the 4 C's that you look at when you buy a diamond. Is it cut well, such that you get internal reflection without a lot of leakage of the external light? So I don't know if diamonds are really, civilization changing places where we might look at this. So if we were looking at just a regular wire that suffers from Ohm's law because it's copper, we might have some kind of a signal. We lose voltage along the line due to I squared R, and then the intensity of the signal is pretty weak at the other side. So out in the country, if we're delivering cable or internet, you might have to put up repeaters, something that listens to the signal and then rebroadcasts it or sends it down the next section of wire with a boost. Those are regularly spaced and they are expensive and a pain. What if instead we tried to take advantage of this optical property for light? And I want something where if the light were to enter and come in, and I have a very transparent material that doesn't have a lot of, it's not cloudy, so it's not absorbing any of the light. If it's super transparent, it would be nice if when the light beam entered, I made it bounce off this next wall and not escape. And take advantage of that to just ting, 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 and have that light ray bounce through this entire pipe to some kind of receiver. We can go much longer distances. We don't have to deal with repeaters. This is a very reliable kind of system. That's also really energy efficient. So we might use some kind of a high index for the core and then laminate it with a really thin sheath that's got a lower index of refraction, and make sure we take advantage of this Snell's law phenomenon for total internal reflection. The way these are made, we get a big glass cylinder. It's wrapped with another glass cylindrical shell. They're fused together, and as the glass is heated and extruded or is bent through the spinner, it'll unwind this glass and really like pinch it and stretch it really thin into these kind of cables. And that gives it a little thin layer. And you don't need much, just enough at the surface to make sure that we get this transmission. These can be defeated if we're not careful. So not every wire that you need to lay will go in a straight line. At some point it'll have to bend. If we keep this radius of curvature fairly large so that we don't foul the incident critical angle, this is fine. We continue to get the light transmitted. But if we're not very careful and make it bend through an angle that's way too steep, when the light hits here, it has the opportunity of escaping. So your telecom people and cable people, if they're laying wire, they need to be careful to know how tightly can you bend these wires without getting that kind of an effect, because we want the light to stay inside. All right, so kind of a more trivial case. Some of us may have these Christmas trees that have fiber optic cables. They look like fishing line, and they're backlit. And then when they're lit up, here in the base, the light's transmitted directly to the ends, and it escapes from the light pipe from there. These are a case where you can see the total internal reflection at work, because these really shouldn't be glowing red. They should look transparent and should look dark. If they are a little hazy, it's because it's not really a very good, highly optically transparent plastic. Although sometimes you might want those defects in it. So I've got a version of these that's crimped, right? They just took pliers or something and crushed the cable at regular spots along its length. Well, if there are defects there where the light is hitting at a weird angle, then it's possible for the light to escape from these. And it just kind of changes how much of the light, how many of the lights you see. Instead of really bright ones at the ends, you get slightly less bright ones all around the surface. All right, so let's do kind of a fun example, just because we should. My physics professor when I took EP2 was a character. So he and all of his grad student buddies, who were all physics grads, were on spring break somewhere in Florida near a beach. So my professor wakes up and he can hear gunfire. And he looks around and gets out of his tent, and he sees his roommate at the edge of the pier, because this was a beachside kind of place. And he's crazed in his underwear with a handgun, firing a revolver at a shark. And I don't know why it was so important to take this shark out. Maybe it was like some insane crazed shark, or maybe it's some kind of land shark, because the shark is in the water. It's not coming out, but whatever. So here's our insane frothy mouthed shark. What's the advice that you might give to my professor's roommate? You hear this, you run out screaming. What should you say? Something like, aim lower. Right? The brain is a little bit stupid about this. It sees the image because it's traced this ray backwards, assuming its source is a straight line away. But what do you know is happening here? The reality of the case is this light was bent away from its normal line, which means the true shark is somewhere down here. And it's mean. So what do we need to do? Aim this not directly at the image. You need to aim it a little bit lower. Okay, so we can just keep that stuff in mind. This is a great conceptual kind of question that you might see. And if you have someone who likes to torture you like I do, I might even try to give you like a trick question. So let's look at it in two different cases. Case one, you have this situation, you've got a shark that needs put down. And your tool is a 1953 Romanian-made copy of a Soviet TT Tokarev pistol. The bullets are not going to experience Snell's law. So what do you need to do? Aim lower. And this would be true for anything that fires projectiles like this. We got bullets, you're throwing rocks, arrows, slings, harpoons, whatever, right? Spears, you name it. Aim a little bit lower to hit the object where it actually is. Let's try to flip this on its head and say, what if instead I was using a 2633 or 2366 Starfleet Type 2 hand phaser. It's a directed energy weapon. And for you nerds who realizes this fires nadion particles and is a particle weapon, you're blowing the demo for everyone else. So just assume it's like a laser weapon that would fire EM radiation. Where would you aim the phaser in this case? You'd aim it directly at the target because the beam is going to hit the water. It's going to bend inward according to Snell's law. And we would see, the beam is directly on the image. So when we're talking about stuff like in your future weapons, this is maybe an interesting consideration to think about. If, say, you were going to program some kind of video game in the future that would have, the difference between pipe guns and laser weapons, maybe you would want to take this into consideration and make something that was really, truly neat, where you'd have to adjust your drift for these kinds of physical considerations. So just something to think about.